Assalamualaikum warahmatullahi wabarakatuh and salam sejahtera. Right, today we are going to learn on a new chapter, which is chapter 2 on matrices. Alright, so today I will cover the first three subtopics in matrices, which is the first one, introduction, okay, and then followed by type of matrices, and lastly is operation. So in part 1, we will cover these three subtopics. So first question, what is matrix? So matrix is a rectangular array of elements or entries, Aij, involving m rows and n columns. Okay, so we denote A, matrix A, by using the capital letter. Alright. For example, here we have capital letter A. So this is matrix A. Okay, and we name the matrix based on the columns and the rows. Okay, so how many rows does the matrix has, and how many columns does the matrix has? Okay, so we name it first by mention the rows. Okay, followed by the number of column that the matrix has. Right? So for example, if we have matrix A 3 times 3, it means here that we have 3 rows and 3 columns. So matrix A will look like A, B, C, D, E, F, G, H, I. If we have another matrix such as matrix B, okay, we name it as 3 times 2, means here we have 3 rows with 2 columns. So our matrix may look like this, for example. So 3 rows, we will have 3 rows. Okay, so A, B, C, but we only have 2 columns, so means we will have like 2 columns here. I put D, E, F. Okay, so we have 3 rows, 2 columns. Okay, so this is 3 by 2. This is 3 rows, 3 columns. So this matrix A is 3 by 3. Okay, so that is how we name the matrix. Right. So each of the letter here, so each of the letter here, okay, inside the square bracket here, okay, we call it element or entries. Alright, so you can say you can call elements or entries of Aij, because we use capital letter A, so the element, it is easier for us to just write it as a small letter A. Alright, so here the first entry, okay, we name it the same way we name the matrix. Okay, what I mean here is we name it after row and column. Okay, but row here, okay, is I, and column is denoted as J. So I is row, C is J is column. Alright, so this is element first row, first column, because this is the first row and the first column. Okay, so this element is called element 2 by 2. Okay, element 2 2, because it is second row, second column. Right, so this is second row, and second column. Okay, so this element is located in the second row. This is second row. This is the first. This is the second row, and the second column, because this is the second column. So this is all the elements for the second column. This is all the element for the second rows. Okay, so this one, this element is element 3 3, because the I, which is the row, is the third row, and the J is the third column. Okay, so it is third row, third column. Okay, so this one, this is element A1 3, because it is in the first row in the third column. Okay, so A1 3. Right? So whenever your I is equal to your J, means the element of row equal to column. Okay, for example, this one, this one, this one. Okay, all the element here until here, where at the end here I is equal to your J. Okay, this is called diagonal. Okay, this is diagonal element. All of this is a diagonal element. Okay, so this is diagonal elements. Now let's say if we have two matrices, we have matrix A, okay, where matrix A is matrix M by N, okay, and we have matrix B, where matrix B is matrix R by S. Okay, so here M is rows and is column. Okay, same goes here. R is our row and S is our column. Okay, matrix A and B here are said to be equal whenever they have equal row. Okay, equal rows and they have equal column. For example, if you have matrix A, B, C, D, E, F, G, H, I, okay, where this is 3 by 3 because you have 3 columns, 3 rows, okay, 3 rows, 3 columns, okay, and matrix B also have A, B, C, element A, B, C, D, E, F, G, H, I, okay, so where matrix B also has 3 rows, 3 columns. So here they have equal rows, equal columns, and this matrix A and B are said to be equal where all the elements inside are also equal. Okay, we can say that the elements are equal. If A here, element A here is 1, element B, A of the matrix B also 1. Okay, so if the element of F here is 5, okay, whenever matrix A and matrix B are said to be equal, F of the element A also should be 5 because they are said to be equal. Okay, and if aij for I that is equal to j, so where the row of the elements and columns of the elements are equal, then the entries are called diagonal. Okay, so diagonal is the matrix in the like this is A11, A22, A33. So this is 1 2 1 3 2 1 2 2 2 3 A31, A32. Okay, so you see here the I and the J, the I and the J, the I and the J are equal. So I equal to J. Okay, when I is 1, J also 1. When I is 2, J also 2. When I is 3, okay, third row, J also third column. Okay, so all these element is a diagonal of matrix A. Okay. Let us look at example here. Okay, we find the values for the variables so that the matrices in each exercise are equal. Alright, so it is mentioned here that the two matrices are equal. Right? So whenever it say equal, it means that they has equal rows, equal column. Okay, so that all the elements inside the matrices are equal. Alright, so here you have 2 by 2 matrix because you have like 2 rows and 2 columns here. Okay, same goes to this the other side. Okay, this side where the matrix is also 2 by 2, where you have 2 rows and 2 column. So they have equal row and equal column. So we can say that these two matrices are equal so that all the elements inside here are equal. So element of A11 here equal to the element of B11 here. Okay, so A12 here equal to the element of B12 over here. And element A21 here equal to the element of this B21. Okay, this is element A22 equal to element of B22 here. Alright, so we need to find that the unknown here. We have like 3 unknown here, which is X, Y, and Z. Okay, so by using the definition of these two matrices on the right hand side and the left hand side are equal, so that we can form 3 equation here where X is equal to 12. Okay, so we can get directly the answer directly from here. Okay, element this equal to element that. Okay, so for this one is equal to this element. Okay, this is our first. Our second is y plus 3 is equal to 5 here. So this is our second equation. So we can solve it on the spot. So where y is equal to 2. Okay, and then the third equation is this one. This element equal to this element. So 2z equal to 6. This is our third equation. So z on the spot is equal to 3. Alright, you can check your matrix by substituting all the value of x, y, z into this matrix and make sure matrix on the left hand side, okay, the elements are equal to matrix on the right hand side here. Okay, let us substitute. So x is 12, correct? So when y is equal to 2, so 2 plus 3 is 5. Okay, z here is 3. Substitute into here, so 3 times 2 is 6, and 8 is 8. So this is the matrix on the left hand side after the substitution of the x, y, z, and it is equal to the matrix on the right hand side, which is 12, 5, 6, 8. So this matrix, both matrices satisfy the definition. Now let's go to types of matrices. Okay, so I will introduce type of matrices one by one. So the first one is a square matrix. Okay, what is square matrix? Square matrix when the number of column equal to the number of row. Okay, so this is remember before this we name our rows, we denote our rows as M, and we denote our column as N, right? Where matrix is named after M by N, which is row, column, right? Okay, whenever number of your number of rows equal to your column, okay, what is column? Column is N. So row equal to column, which is N. Okay, so the matrix is N times N. This is called square matrix. Okay, for example, you can look at here. We have matrix A here. We have 2 rows. Okay, and we have 2 columns. Okay, so here row equal to column. Okay, so this is square matrix 2 by 2. This is also square matrix because you have 3 rows, okay, 3 column. Okay, so 3 by 3. When number of row equal to column. Okay. Second type of matrix is diagonal matrix. Okay, we call this diagonal matrix because we only have the element of the diagonal part. Okay, while the other elements are 0. Okay, so only the diagonal contain the non-zero element. Okay, while the rest of the elements are 0. So this is called diagonal matrix. Whenever your matrix is a diagonal matrix, okay, but with all the elements are equal, okay, this is called scalar matrix. Okay, so just now you have, for example, you have matrix A with this. This is called diagonal matrix because you only have the element for the diagonal part while the rest of the elements are 0, right? This is called diagonal matrix. But whenever all the diagonal elements here are equal, such as this and this, okay, this is called scalar matrix. Okay, can you see the difference? This is diagonal matrix because all the elements at the bottom part and the upper part here are 0. Okay, so you only have the elements of the diagonal part. So this is called diagonal matrix. But whenever your matrix is diagonal and okay, with the elements of the diagonal are equal, okay, this is automatically called scalar matrix because you can factor 2 out so that you have this with where your A, matrix A is a scalar matrix with the scalar 2. Okay, your K, your scalar is 2. The fourth matrix is called identity matrix. Okay, so for identity matrix, okay, it is a matrix whenever all the elements of the lower part and the upper part, okay, the lower part and the upper part are all 0, and all the diagonal elements are 1. Okay, so 1, 1, 1. This is called identity matrix, or we write as I. Okay, we denote as I. This is called identity matrix. The fifth is zero matrix. So when it is mentioned as zero matrix, means all the elements are 0. Okay. Let's say if you have matrix A like this, okay, and you want to find the negative matrix, okay, you just multiply negative to your A, okay, to matrix A, you get -1, 0, -2, 0, 0, negative times negative will be positive, positive 3, so negative times -4 will be positive 4, and negative times 6, it is -6 and -1. Okay, where this is negative multiplied to the matrix A. Okay, so this is negative matrix A. Whenever at the bottom part, okay, of the matrix are equal, okay, where you only have the element for the upper part, okay, this type of matrix is called upper triangular matrix, okay, upper triangular matrix, because you only have the upper part element, okay, so you have the upper part element only, while the rest of the elements at the bottom, they are equal. Okay, at the bottom here means below the diagonal, so this is the diagonal element, right? Okay, so once all the element below the diagonal here are all 0, this is called upper triangular matrix. Okay, contradict to the matrix before this, okay, whenever you only has the element below the diagonal, okay, this is the diagonal element, so you only have the element below the diagonal, while the upper element are all 0. This is called lower triangular matrix, because you only have the element for the lower part. Okay, so this is lower triangular matrix. So next type of matrix is transpose of the matrix. Okay, I don't want to read all the definitions here because it is difficult to remember. Okay, so I just really explain what is transpose of the matrix. Okay, transpose means you change your row become column. Okay, so row change to column means you need to rearrange all the element here. Okay, the row you swap, okay, you write it as a column, and for column you write it as a row. Okay, so for example, you have matrix A here, okay, with all these elements or the entries. Okay, so you want to find the A transpose, where we denote as A T. T here means transpose. This is transpose. So A transpose matrix A, we transpose it. Now look at this. This is your first row. Okay. So all the horizontal elements here is your first row. Now all the first row here change to become first column. So first row now become first column. You see, so 1, 1, 1, 1, 2, 2. So all the first row element now has become first column. Okay, now the second row, okay, this is second row. All the second row here, the horizontal part, the second horizontal, okay, you change it to become second column. So negative 2, negative 2, 1 become 1, 5 here. So now it becomes second column. Okay. And then the third row, okay, make it as your third column. Okay, so 3, 3, 4, 4, 1, 1. Okay, you see? Or you also may start by using the column. Okay, you can also start by using the column. So this is your first column. Okay, when you start by using column, you must change column to row. So the first column become your first row. Okay, where is the first row? Here. Okay, so 1, 1, negative 2 become this, and 3 be there. Okay, same goes to second column. It will become your second row. Third column will become your third row. Okay, so it doesn't matter if you want start to change the row to the column, or you want to start by column change to row. Okay, as long as that is the way you transpose it. Okay, let us look at the properties involving the transpose matrix. Alright, so let's say if you transpose the matrix and then you transpose once again, that will be equal to the original matrix. Alright, and if you have a scalar key multiplied to the matrix A, and then you transpose that matrix, that is equal to, you transpose the matrix first and then multiply with the scalar later. Alright, and if involved with the addition and subtraction of two matrices, and then you transpose the summation or the product from the two matrix, okay, that is equal to, you transpose the matrix respectively, and then you perform the addition and the subtraction later. Okay, so let us look at one example, just a simple one. Let's say you have a matrix A here, where A is 1, 1, 2, 0, 1, 3, 4, 1, 2. So you have matrix 3 by 3 here. You have 3 rows with 3 columns. Okay, and then you transpose this matrix, that is equal to A transpose here. You transpose it. I choose transpose the column to become row. Okay, so 104 will become 104 row. Okay, so second column 111 will become the second row 111. Okay, and this is the third column will become the third row 2, 3, 2. Okay, now this is A transpose, which is the one inside the bracket, right? Whenever I transpose this one more time, okay, so I transpose this one more time, okay, I will get the original matrix. Okay, let us see. I transpose the first column, so it become our first row 1, 1, 2. Our second column 0, 1, 3 will become second row 0, 1, 3, and then our third column will become the third row, which is 4, 1, 2. Okay, compare with this one. Are they equal? as they are. So that is the proof of A transpose. When you transpose it one more time, you will get the original matrix, which is matrix A. Okay, so by using the symmetry A here, okay, let's say you have a scalar k equal to 2, you multiply to A. Okay, so I multiply first to A, okay, 2 to matrix A, you get 2, 0, 8, 2, 2, 2, 4, 6, 4. Okay, and then I transpose this matrix, okay, to A transpose. So I will get 2, 0, 8. So the first column will become first row. Second column 2, 2, 2 become second row. 4, 6, 4. The third column will become third row. 4, 6, 4. Alright. So this is this side. Okay, let us perform this. We transpose first. Okay, where is our A transpose? A transpose is just now this, right? Okay, we multiply with scalar k. K is 2. 2 multiply here. What do we get? 2 times 1, 2. 2 times 1, 2. And then 2 times 2, 4. Okay, so we get similar answer. Alright, same goes to this. You can try this by yourself. Let us look at example 1 here. Okay, so we have two matrix, matrix A and matrix B here, where matrix A is 2 by 3 because we have 2 rows with 3 columns, and for matrix B we have 3 rows with only 1 column. Okay, so the first one we need to find the A transpose. So this is our A. We transpose each of the row here to become the column. Okay, so now A transpose is, so let us transpose the row to column. So first row become the first column. Okay, and the second row will become the second column, which is 4 minus 5 and 2. So this is A transpose with matrix 3 times 2 because we have 3 rows with 2 columns. Okay, so next is negative 2. So we have a scalar k equal minus 2. We multiply to B, and then the product we need to transpose it. Okay, so if we multiply minus 2 to our B here, okay, so 2 minus 2 multiply with this matrix, so you will get 2 times 1 is 2, 2 times minus 3 is minus 6, 2 multiplied with 2 is 4. Okay, so it does not change anything. It is still 3 by 1 matrix because you only times the scalar to the matrix B. Okay, so before I proceed to third example, please take note that if you want to perform the addition or subtraction of two matrices, okay, please make sure that they have equal dimension. Okay, what I mean is make sure that they have equal dimension, means equal row and equal column. Okay, where this column should be equal to that column and this should be equal to that. Okay, so row must be equal, column must be equal. So in this case, A and B, you cannot perform addition and subtraction because they have different dimension. This is 2 by 3, this is 3 by 1. So they have different columns, okay, different number of column and different number of rows. So it is impossible for you to do the addition and subtraction. Okay, that is one thing. The next thing is when you want to perform the multiplication of the two matrices, alright, you must make sure that the column of your first matrix, okay, is equal to the row of your second matrix. Okay, so if they have equal number, then you can perform the multiplication A and B. If not, if they are not equal, you cannot perform A multiply with B. So A and B is impossible to perform. Alright, so whenever you can perform A and B, okay, in which they have the first matrix has equal column to the second row of the second matrix, okay, you should expect that the product of the two matrices is 2 by 1. Okay, 2 by 1. Right. So for example, if in this case, okay, these two matrices, you cannot perform the multiplication. You see, this is 2 column, the number of column is 2, the number of row is 3. So they are not equal, so you cannot multiply this. Alright. Other example, you can do the tutorials, and from there you will understand what I mean. Okay. Alright, so for AB here, what we can do is if you transpose the matrix, okay, from matrix A, and it does not change anything, what I mean is you get the similar matrix, okay, that is called symmetric matrix, because no matter how you transpose row to column or column to row, you still get the same matrix. Okay, for example, like here you have matrix A, and then when you transpose the matrix A, okay, you see when you transpose the column to row, 514, 514. Okay, you transpose the second column to row, you still get 1, 2, minus 2. 1, 2, minus 2. Okay, you transpose the third column, you get the third row here, which is 4 minus 2, 3. 4 minus 2, 3. And when you compare each of the element contained in the A transpose here, they are similar to the element in A. 5, 5, 1, 1, 4, 4, and so on. Okay, so in this case, your A transpose equal to your A. This is called symmetric matrix. Okay. Okay. Next is when your A transpose is equal to the negative A. Okay. So that is called skew symmetric matrix. Okay. You must make sure that you can recognize all the types of matrices. Alright. Okay. So for example, you have this matrix A. So let us transpose matrix A. So transpose the first, so become the first row. So 0 minus 1, 4. So the second one here, 1, 0, minus 7. And the third one here is minus 4, 7, 0. Okay, so that is your A transpose. Let us look at minus A. Minus matrix A, so you get 0. Minus minus is positive, so minus positive minus. So this is minus positive. This is positive minus. Now let us compare each of the element in A transpose and negative A. So you will get similar. 0, 0, negative 1. This is also negative 1. This is 4. This is also negative 4. And if you check all the elements in these two matrices, they are equal. So here what we can conclude, A transpose equal to the negative A. This is called skew symmetric matrix. Okay, so if you were asked to prove that A transpose is if your A is skew symmetric matrix, what you need to do is you need to prove that your A transpose equal to the negative A. Okay, once you can do that, you can prove that matrix A is skew symmetric matrix. Understand? Okay, this is the working or the step that I did in the previous slide. So they are equal, so I just skip this slide.